So we're recording now, so let's be serious. So conditional probability. We mentioned what is conditional probability last time. And if you've seen my videos, and you can play them, the recommended speed to play my videos is at 1.4, 40% faster, because I talk slowly. If you're used to people who talk very fast, actually the voice even sounds better. Goes a pitch up, but sounds better. Anyway, conditional probability. So the definition is the following. I have A, which is an event. We spoke about it last time a little bit. And B, which is the condition. So the condition, when we say a condition is something that has already occurred. We take it as a given. Yes, it's going to be on Blackboard. So this is equal to the probability of A intersection B. The condition can also be used as an event divided by the probability of B. Okay? So that's exactly the definition of conditional probability. And the effect of conditional probability of introducing a condition is that essentially, if this is your event space, the condition truncates the event space, so it makes it smaller. So that becomes the event space. And if A is an event, then the graphical interpretation of this ratio that I have here is exactly that the probability of A intersection B is essentially depicted by the area that I mark with red, which is the overlap of the event A with condition B. And of course, we don't compare this overlap with respect to the entire event space S, but we only compare it with the condition B. So we divide the red area by the black area. That's exactly what this rule says. And the important thing, which would look dull to my friends who attended the class in the morning, is that I have to go back and talk about this here. So let's read this problem. This is about a department store. Sells sports shirts in 3 sizes: small, medium, large, 3 patterns: plaid, print, and stripe, and 2 sleeve lengths, long and short. So the accompanying tables give the proportions of shirts sold in the various category combinations. Now, how do you go to the next page? Oh, goodness. I think I got stuck. The software is not running properly. So here are those. It was not turning page. Probably it was. Yeah, I went up. I didn't have the arrow to turn the page. So here are those two tables. Can you tell me what do these tables represent? Those are called contingency tables. And essentially, since you have three configuration settings, the short or the long sleeve, the pattern and the size of the shirt, those are the 3 configurations. We have a three-dimensional contingency table, but since we cannot easily depict the three-dimensional contingency table, we do two tables. First floor, second floor. Okay? The one would be on top of the other. Now, if you add all of these numbers here, all of those that exist here, then these numbers add up to 1. And exactly this is the definition. Contingency table is a term that was invented, is a type of table. It's used in accounting, and essentially it was invented in the Second World War for doing calculations, and what it runs is the sanity check. So when you sum the rows or you sum the columns, and then you add the sum of all columns or the sum of all rows, the sum of this, when you do the sums of the sums, they should give always the same number. If they give different numbers, then there is a mistake somewhere. So you have to go back and correct it. So that type of table was being used for accounting purposes. And it's been also adapted in probability theory because you will see where we put the sums in the margins below all rows or to the right of all columns. Then when we do multidimensional variables, we will be calculating there the marginal distributions, the marginal densities. So those are called contingency tables. If you add all the numbers that you see here, the decimal numbers, they all add up to 1. Now, what does it mean? The problem says precisely the following. The department store, the accompanying tables give the proportions of shirts sold in the various category combinations. So what does that mean? Category combinations. If I call event A, that the sleeve is short. Event B, that the pattern is plain or print, or the size is short, or the size is medium, then what kind of events do I have? Actually, I can use my previous, because I solved this problem earlier in my class, so I can use it. So look at these events. A, short sleeve. B1, short style plate. C1, size, short. What is the probability of A intersection B1 intersection C1? What does that mean? That the shirt has short sleeve and plate style and is short. If we go to the table, what's the probability of this? Short sleeve and short size and style plate. It's 0.04. Why? I have to pick it from the first of the two tables because that corresponds to the short sleeve configuration. So this is short sleeve configuration and size, short and size style. So that's a 0.04. So now if I want to calculate the probability, what is the probability that a shirt that is sold is short sleeves? What would I sum? What would I sum if I ask this question? A shirt is short sleeved. From the short, yes, and if you sum them all, we did that in my earlier class, we do 5.56. So now if I say, how do I interpret, based on what I have written, how do I interpret this result, this event here? Here I have a conditional probability. What is the condition? the condition is that the shirt that is being sold has short sleeves. The event is B1 intersection C1, so that means the style is played and the size is short. So if I would to interpret this, I would say this is the event where a athletic shirt is being sold, which has played style, short size, given that the sleeve is short. Or if the sleeve is short. When we use the if or the given that, then we imply condition. We can imply condition with other words, with other type of wording, like using modifiers as well. We can imply condition. So by adding attributes, sometimes we imply conditions and we don't necessarily imply the intersection of events. So we have to be very careful to understand in the wording of a problem whether we have a condition or we use and. We have to use the logical function and. So here's exactly how we calculated this conditional probability. Now let's go back to the problem and do one. Let's answer one of the conditions, one of the questions. Let's answer question D. What is the probability that the size of the next shirt sold is medium? What is the probability that the next shirt size that is sold is medium? How are we going to find that probability? It can be medium with short sleeves, or it can be medium with long sleeves. When I say with short sleeves, what do I mean? And or condition. Yeah, so it's and. Yeah. So a medium size shirt can be short sleeve or not short sleeve. By using the verb can be, I mean and. I add an additional property to that. So that puts me in the second row of each of those two tables. So if we sum the probabilities in the second row of short-sleeved, then that probability is equal to how much? 0.27. And if we do the same thing in the corresponding row of the long-sleeved table, then again we get 0.19. So 0.19 plus 0.27.
Wait. 0.22, right?
Oh yes, 0.22. 0.27 plus 0.22 gives us what? 0.49. Correct? Why did we add the probabilities?
Because it's the union.
Yeah, but why do we add, whenever we have the union of two events, do we add always the probabilities? When do we add the probabilities? When the events are exclusive. Are these events exclusive? Yes, and why? Yes, because the shirt can have either a short sleeve or a long sleeve. We can have both. Okay? That's why we add the probabilities. Is it clear? Now, that wasn't conditional. It was just a question. Now, let's look at that question E. Given that the shirt just sold was a short sleeve plaid, what is the probability that its size was medium? Given that the shirt that was just sold was a short sleeve plaid, what is the probability that the size is medium? Short sleeve plaid. What is the probability that the size is medium? Given that, so what does that imply? Given that.
Conditional.
That's a condition. So the condition is given that shirt is short sleeve and plaid. short sleeve plate. So let's go here and let's work a little bit. So short sleeve and plate. So this is our condition. So this is our B here. This is our condition. A is what, according to the problem? A is size is medium. Correct? And the question is find the conditional probability of A given B. So what is this equal to? This is equal to the probability of A intersection B divided by the probability of B. Now, what is the probability of B? Short sleeve and style plate. So here is the table. Short sleeve and plate puts us in this column, okay? So we have, it can be of size short, medium, or large. So we add the probability. So that the probability of a shirt being short sleeve and short sleeved and plate is 0.15. Correct? So this probability, the probability of B, is 0.15 at the first column of the first plate, the first table. Now, what is the probability of this being medium? And also A intersection B. So what does A intersection B mean? Short sleeve and plate and size medium. So where are we put? Short sleeve and style plate and size medium. That's A intersection B. It puts us in this position of the table, correct? Do we understand that? So that's 0.08. So the probability of A intersection D is 0.08. So the probability of A given B is 0.08 divided by 0.15, 8/15. You see that this probability is significant. It's much higher than the probability of the short being short-sleeved and plate and size medium. Because that was the 0.08 out of 1. Because it was all shirts. When we introduced the condition that we want short sleeves and style plate, that effectively reduced the event space to only these shirts, so the probability went up. And that's exactly the main idea with conditional probability, that if you reduce the size of the event space, then the probability changes. It may go up, but it can also go down. Is it clear? This is a very interesting, this is a problem where you can actually use it to practice a bit. Let's look at question F. Given that the shirt that was just sold was a medium plate, what is the probability that it was short-sleeved? Medium plate. So medium and plate. What is the probability that it was short-sleeved? What is the probability that the shirt is medium and plate? 0.18. Why do we add 0.08 and 0.10? We add them because that shirt can have short sleeves or long sleeves as well. So the probability of a cert being clade and medium is 0.8, 0.08 plus 0.1, that's 0.18. And then, so this is our condition, the probability of our condition. What is the probability that it is short-sleeved? 0.08 divided by 0.18, okay? That's an easy problem. So we understood how we can solve problems using those contingency tables. Now, let's go to problem 51. One box contains 6 red balls and 4 green balls. Let me lift it a bit. And a second box contains A second box contains 7 red balls and 3 green balls. A ball is randomly chosen from the first box and placed into the second box. Then a ball is randomly selected from the second box and placed in the first box. Do you understand the mechanics? We have 2 balls with 2 boxes which contain red and green balls. We take 1 ball from the first, we pick it at random, and we put it in the second ball, in the second box. Then a ball is randomly selected from the second box and placed in the first box. So we end up with the same initial number, but probably different configurations in colors. What is the probability that a red ball is selected from the first box and a red ball is selected from the second box? Okay, here I need to mention a definition, but we'll get into it. We'll get to that. So we pick a ball from the first box, we put it in the second. And then we pick a ball from the second box, which has 1 more now, and we put it back into the first. Is the event of selecting a ball from the first box, and putting it into the second, does this event affect what the second ball?
Yes.
It does. Why? Why?
Well, like if you draw a wet ball, it's going to increase your probability of taking a wet ball.
Okay, if you get any ball that you will get from the first ball, it will change the configuration of the balls in the second box first because it changes the number, and therefore, and also it changes the types, the number of balls, the number of red balls and green balls that you have in the second ball. So one event is influencing the other, okay? These events are called dependent events. So if we go to, let's say that A and B are dependent events. That's not a definition, but it's a heuristic definition. If the occurrence of A influences the occurrence of B and vice versa. Or it would be more accurate to say the way B occurs. B occurs and vice versa. So if they don't influence the way they occur, A and B, then they would be called independent events. Okay, so this is not a mathematical definition, but it's a rule of thumb, a criterion to judge whether 2 events are dependent or independent. Now, we say that A and B are independent events if the probability of A intersection B is equal to the product of the probability of A times the probability of B. This is the definition of independence. And of course, that implies that the probability of A given B is going to be equal to the probability of A. And if you change what you use as a condition, this is what you would have. So this is the definition of independence. That's the mathematical definition of independence of two events. If two events are not independent, then we call them dependent. But the question is, the mathematical definition cannot always help us to understand whether two events should be treated as dependent or independent. This rule here helps you to understand when you will treat two events as independent or not as independent. In statistics, that's something we cannot cover in this course. We typically don't have the time to reach that point. We judge the independence of events based on a statistical test which is called rank sign test or Wilcoxon test. We use those non-parametric so-called tests, which are tests for independence of events, and that's exactly how we can mathematically assert independence of events. In this course, we will not be doing that. We will try to understand whether there is mechanical independence or dependence between the events. The way one will occur will influence the occurrence of the other. Okay, that's how we'll do it. So here, those balls clearly affect one another, the way we will do them. So let's go back to this and call in this problem A, select a red ball from box 1, and B, select a red ball from box 2. So the first question is asking what's the probability of A intersection B? And the way I'm going to solve the problem is to, first of all, scroll up and use this formula. Now let's see what this formula gives me. This formula gives me the following. It implies, because it's an equality, that the probability of A intersection B is equal to the probability of A given B times the probability of B. And it's also be written as the probability of B given A times the probability of A. I choose whichever I prefer, whichever of the two right-hand sides, depending on the circumstances of the problem that I solve. And this will become immediately clear. So I'm going to my problem here, and I will use what is my condition, what is the event that I'm looking at. The event that I'm looking at is A intersection B. Which is the event that occurs second in the row? B or A? B, because we select a ball from the second box after we have placed a ball inside it from the first box. So since B occurs second, A will be used as a condition. So I will say that this is the probability of A given the condition A times the probability of A. That's how we should do it. Is it clear?
I have a question. What would that be towards A intersection B?
It's exactly stated in the problem. That's the question we're asking. What is the probability that when A intersection B, a red ball is selected from the first box and a red ball is selected from the second box?
How would it be possible?
No. First you take the bread ball from here, from box 1, and you put it inside. You take a ball from the first box. Now, I don't know if that's red or green. And you put it in the second box. Actually, yeah, the event should be red. And then I take a ball. I select randomly from the second box a ball. The event of interest is that this ball is red. And I put it back into the first. That's the event. Okay, so what is the probability of A intersection B? Here, what I'm using is the universal rule for the calculation of the probability of A intersection B. This rule works always. This rule here, which is more attractive, works only if you have independence. But this is universal. So I don't want you to use this rule, especially when you have dependent events, which you should not do that. So here I'm using this. Okay, let's see. What is the probability of A? What is A? Select a red ball from box 1. How many red balls do we have in the first box? We have 6 red and 4 green, a total of 10 balls. So what is the first probability equal to? Probability of A? 6/10, because we have 6 red balls out of 10 and we pick one randomly. What is the conditional probability B given A? What does that mean now? B given A. What does A mean? We have selected a red ball from the first box and we have placed it into the second. That's what A means. Condition A means. That the ball we picked from the first box is red. What did we do with this ball? We put it into the second box. So how many balls does the second box have? Now it has 11. And how many red balls does it have? It has 8 because it originally had 7. We added one more because that's condition A. So it now has 8 balls. So that probability here is 8 out of 11. The product of these two probabilities, which is 48 over 110, is the probability of A intersection B. Do you understand how I solve the problem? Now, what's the main thing that you have to take home from this? The universal rule for calculating the probability of intersection of two events. Yes?
Are we allowed to assume that it's a given that the first ball picks is red? It was in the problem.
It's in the problem. The problem says, that's a good question. I want to go back into that. The problem says a red ball is selected from the first box and a red ball is selected from the second box. So how can you select a red ball from the second box? You do it after the occurrence of the first event, in the sequel of the two events. What is the first event that has occurred? You placed a red ball, you picked a red ball from the first box and you placed it in the second box. That's why this becomes the condition. In this problem, you cannot reverse what is condition and what is an event, because one occurs prior to the other. There is a time sequence that you have to respect, which clearly identifies which is condition and which is event. In other problems, sometimes you can interchange the roles. Let's work on question B. At the conclusion of the selection process, what is the probability that the numbers of red and green balls in the first box are identical to the numbers at the beginning? Okay, now we have to think like engineers. This is the following. I would answer this question is the following. the probability that numbers of red, green balls in box 1 don't change is equal to the sum of the probabilities that a red is picked from 1 and a red from box 1 and a red is picked from box 2, plus the probability that a green ball is picked from box 1 and a green is picked from box 2. Why do we add the probabilities? Why is this event exclusive from this event? What? We add the probabilities because, of course, it's all, yes. The ball that goes back and forth is either red or green, okay? But why are the events exclusive? To add the probabilities, I need the events also to be exclusive.
Because if you pick a red, then the only thing you can't pick is a red.
Because one event is basically red and red. Red goes to box 2 and red goes from box 2 to box 1. The other is green goes from box 2 and from box 2 to box 1. And red and green, the ball cannot have two colors at the same time. We assume that those balls have only one color. Like that's why the events are exclusive. So what is the probability of the second event? We have to calculate the same way. So what would that be? The probability that a green is picked from box 1 and, I'm stressing the end, a green is picked from box 2. That would be the probability that a green is picked from box 2, given that a green is picked from box 1 times the probability that a green is picked from box 1. So the second factor would be 4/10, okay? We had 4 green balls. Now, in the second box, we have already 3 green balls. Okay? Now we add one more, then will be 4 out of 11, 4 out of 11, and therefore this would be 16 out of 110. So, the probability that we were asked to find is the sum of the probabilities that we have already calculated, 48 divided by 110 plus 16 divided by 110, which gives us 64 divided by 110. Did we understand this nice problem? Questions? No questions? No questions. Those are not difficult problems. Let's work on a different one here. Let's look at 52. Or let's not look. I want to do a problem with independent events. And I don't have a lot of time to find it now, but I will describe it. Okay, now, you know, when aviation first started, planes were single-engine planes. Why? Because they couldn't fit more due to the weight. But when engines started becoming a bit stronger and the plane frames became stronger as well, we put more engines. Why did we go to a multi-engine configuration? What was the main main engineering reason for going into a multi-engine configuration? Correct. If one fails, the other is not going to fail at the same time, or at least so we hope. And the other thing is that even if you use the steering, you can still use differential power for the steering. So by having more thrust in one engine, the left engine, you can turn right. By having more thrust on the right engine, you can turn left. That's differential thrust. And it's a way that also, the same rules also apply in navigation in water, because both are, water and air are both fluids, the same type of things, same mediums. So the multi-engine setting was used for reliability, for increasing reliability. You can stay aloft with one engine, and you can land because gravity will help you to land anyway. You cannot take off with less engines than your configuration because you need the full thrust. So what is if the probability, suppose now why do we have two engines? We're back down from four engines. Why do all modern planes have two engines except 747? One is weight, engines are also bigger. Or why do they have two engines? You conserve gas, yes. Another reason?
Better reliability.
They have higher reliability. So engines are now more reliable, so now you can go down to two engine configuration. And that's why you see the engines being more close to the fuselage, because they can be used for, they can help you with steering a bit more. So what is this based on? If you have, let's say, a plane with two engines, and the probability of an engine failure, a single engine failure, is 10 to the fourth, 10 to the negative fourth, what is the probability that the plane crashes due to engine failure? What does that mean, the plane crashes due to engine failure? It means complete loss of thrust. So how can you lose thrust if both engines fail? Okay, so that is the probability that both engines fail. Now, what do we assume here? Here we assume that this is equal to the probability that engine 1 fails and engine 2 fails. And now we'll assume independence of these two events. Why do I assume independence of these two events? Is this a natural assumption? It is in all aspects a reasonable assumption, unless there is something with your fuel. Okay, so if your fuel tank doesn't give you the proper fuel, then both of your engines will fail. It has happened once. Or if there is a common factor between engines, a common maintenance factor that affects the operation of these engines. So if none of these occurs under normal circumstances, the failure of one engine should not affect the failure of the other engine. It's like at your home. Not all of your light bulbs are going to go out at the same time, unless there's an outage. Okay? That's independence. So by assuming independence, then what is the probability of this event? We multiply the probability that engine fails square here, so that's 10 to the negative 8. So that's how you increase reliability using the rule of independence. And so when both engines fail, that means that something has violated the rule of independence, because the occurrence of a very, very unlikely event is something that cannot be attributed to random events, but rather to a pattern that leads to an event, which actually forces the rule of independence to be violated. Okay, well, these were the things for today, and you have a small homework for Thursday.
What's going to be the number for the next lecture?
What?